Okay, question 4 on this exam asks us to compare a pair of molecules or ions and to describe the pKa's of each one, to list the pKa's of each one, and then to try to explain why one was more acidic than another using one of the 6 factors that affect acidity that we described in lecture. So it's really important to know the 6 factors that affect acidity. If you don't have those in your memory banks, it might be hard to construct an answer here. The first pair would be H2S versus HCl. So HCl is one of our very common ones. You should know that pK equals about -7 for this one. H2S, you think, how does this relate to that? Well, the atom directly bonded to the hydrogen is different. They're both in period 3, so they're about the same size. Sulfur is less electronegative than chlorine. So remember, if we're comparing things in the same row of the periodic table, sizes are going to be similar, but electronegativity is going to be different. So electronegativity is the big difference between these two. Chlorine is more electronegative than sulfur, so HCl is more acidic. And so if you compared, say, fluorine to oxygen as you go from HF, if you needed to make a prediction, HF going to H2O, you go from pK equals 3 to pK equals 16, you'd expect this to be about 13 units higher. So pK equals 6, question mark. Again, you may not have known the pKa of H2S from your studies, but if you compare where electronegativity makes a difference among our standard molecules, and then move the same amount going from group 17 to group 16, just like we did here, increase 13 pKa units. We estimate about pK equals 6. It's really 7, so it's pretty good. So anything in that ballpark, you know that the HCl should be more acidic, the H2S should be less acidic due to the electronegativity difference between chlorine and sulfur. So super nice. And then pH3 versus NH3. Again, you may not remember the value for pH3, but the NH3 is certainly pK equals 36. And the thing that's big difference here is these guys are in the same column, so group 15, and nitrogen is smaller than phosphorus. So that's our clue that size is the big factor that's the difference here. And where we normally illustrated size was HF versus HCl. So HF was about 3, and HCl is about -7. So going to the bigger atom increases the acidity by about 10 units. So you'd say phosphine might be pK equals about 26, which is right in the ballpark of what it is. So understanding these principles helps us to make good predictions. Again, even if you didn't get quantitative on this, you should know that phosphorus is larger than nitrogen, and the larger atom attached to hydrogen makes the hydrogen more acidic. Right, so hopefully knowing things are in the same column of the periodic table, it's easy to predict which atom is bigger or smaller that's directly attached to hydrogen. The next comparison, Ch3 Ch2oh, and this one we should know very well, acetic acid versus Ch3 Ch2oh. This is a comparison straight from lecture that ethanol should have pK in the neighborhood of 15 or 16, similar to water or methanol, and acetic acid pK equals about 5, 4.74, And this carbonyl here allows resonance in the conjugate base. This is resonance where the more acidic compound has more resonance. And what I should be doing is circling boldly the more acidic of each of these. And here I circled the H2S to just highlight it before. If I'm doing that in my mind, I have to remember the instructions were to circle the more acidic compound. We're going to have to go back and double check to make sure we circled the HCl and uncircled the H2S. That's more acidic. Phosphine is more acidic than ammonia. And then acetic acid is more acidic than ethanol. And each one of these factors hopefully clearly explains why one compound is more acidic than the next. And then if we go to H3O plus, again, very common, straight from lecture, versus H2O. H2O, pK equals about 16. H3O plus, pK equals minus 1.7. This one is much more acidic. And the thing that I would say is charge is the thing that separates these two. Some people would say degree of protonation, which affects the number of hydrogens in the charge. Charge is universally a very important concept in physics and chemistry that you should understand. And the positive charge is more acidic. The positive charge compound is more acidic than the neutral compound. So the positive charge ion is generally more acidic than its neutral compound counterpart, as long as other factors are the same. So the fact that hydrogen is directly bonded to an sp3 oxygen in both cases is really important, because otherwise another effect might take over compared to charge. But everything else is pretty much the same except the charge, so it makes charge the defining characteristic here. And then the last one, we have CH4, or one of our very least acidic compounds, pK about 50. And then if you throw in some fluorines that are not directly attached to the hydrogen, then you're going to make it more acidic. This is one other lecture comparison. Here the pK was about 27 to 29. And this is the inductive effect. So electronegative atoms not directly attached to hydrogen make the compound more acidic. So the trifluoromethane is going to be more acidic than the methane due to the inductive effect of the fluorines removing electron density, making the hydrogen more positive. So that's it. Another question just knocked out in a few minutes. And hopefully this made sense. What's the one effect that we didn't talk about? We had the inductive effect, charge, resonance, size, and electronegativity. The one we didn't talk about was hybridization. And so there wasn't really a pair of examples here where hybridization was the most important difference. But that's one you should be familiar with as well.